Welcome to the exercises for Chapter 3. This video is for exercise 1. Earlier in this chapter, I described the differences between linear and nonlinear functions, and the key difference is that a linear function has constant change over the x-axis. So the changes in the function over the x-axis are constant. On the other hand, nonlinear functions change dynamically over the x-axis. Sometimes the functions change a little bit, sometimes they change a lot, and that is a nonlinear function. Okay, and that in turn leads to the concept of the derivative, which you'll learn about in later chapters. Okay, so the goal of this chapter is to examine two functions. So we have function f1 and f2. f1 is defined by 2x and f2 is x squared. Okay, so two simple functions. And the first goal is just to implement these functions in NumPy and then plot them on the same axis like this. So you can see that the domain goes from -2 to +2, and I simulated 101 linearly spaced points between -2 and +2. So here's the function 2x, and then here's the function x squared. Next, what we want to do is compute their successive differences. So within each of these functions, what is the difference between each point and the previous point? Okay, and that is what we see over here in panel B. So these are the differences between successive x-axis values and the functions for those successive x-axis values for these two different functions. So this straight line here is for function f1. And you can see that that line doesn't change over the x-axis. That's because this function, the function itself changes, but the way that it changes is constant over the x-axis. So it's always increasing by the same amount. So therefore, the point-to-point changes are constant. And here we have the function x squared in the dotted lines, and that function changes as a function of the x-axis. So it decreases here, and then it's not moving at all around here, and then it starts to increase over here. And that's what we see here. So from point to point, the function is getting negative. So each successive function value is negative, and then here the function is increasing, so each successive point is positive. Okay, we want to do this twice. So calculate these differences twice. Once using a for loop, where you loop over all of these 100 x-axis grid points and compute the difference between each function value and the previous function value. And then you want to implement it again without using a for loop, using vectorization. So there's a little bit more to this exercise, but first I'm going to switch to Python and show you the solution to creating this figure here. Here is where I define the x-axis grid, so -2 to +2 in 101 points. And here I have the functions, so 2x and x squared, very simple. Here's where we compute their differences. So I mentioned to do this twice. So the way that I solve this is to have function f1 calculated in a for loop and then f2 vectorized. So in the for loop, we loop over all of the x-axis points, and then we calculate the difference. I call this variable dy. This is the difference between each function value and the previous function value. That's why we start at index 1 and not at index 0. And then here we have dx, and that is the x-axis value for this value versus the previous value. And then we have the differences is dy divided by dx. So the change in the function divided by the change in the x-axis. Okay, so that is one method, and then you can do this also vectorized. Now, the functions here are different, but the calculation, the code is the same here versus here. Here, this is just vectorized. In general, whenever possible in real-world coding, it's good to use vectorization instead of for loops, but I think there are many situations in when learning math and when learning coding where it's actually better to use a for loop when that helps you understand the mechanism, even if that makes the code a little bit uglier. And this code tends to be longer and takes more compute time and so on. But anyway, this is how we're doing it. Okay, so then, the rest of the code here is very simple. That's just visualizing the objects that I have created here. Again, the point is that A linear function is a line, and so the function itself changes over the x-axis, but the way that it changes, the rate at which it changes over the x-axis is constant. That is always the case for a linear function. It's not always a value of 2, but it's always going to be some value for a linear function. A nonlinear function, the way that it changes over the x-axis changes as a function of where you are in the x-axis, and that's what you see here. So any nonlinear function is going to have a non-constant representation in a differences plot like this. It's not always going to be a straight line. It could be a curve, but that depends on the particular values of the function. So now we have two follow-up questions now that we've created this graph. Question 1 is, do the differences values depend on the x-axis resolution? So we used 100 points or 101 points between -2 and +2. And do these graphs change when we use a resolution of, I don't know, let's say 30 points or 3 bajillion points or something? So that is what we are going to explore in the code. And then question 2 is just observing that although the function values change over the x-axis, delta x, which is the x-axis resolution, never changes. And that's because we have linearly spaced points between -2 and +2. So from point to point, the function changes on the y-axis, but from point to point, the change in the x-axis is always exactly the same. Okay, so then the question is whether the delta x term is even necessary in the code. And what happens when we exclude delta x? Does that change anything in these plots? So for the first question, what I'm going to do is change this. Let's say, make it, I think I said 20 versus 300. So here we have the plot with n equals 20 points, and it looks the same. The values look the same. This was -4 and +4, going back up to 4 over here. And here, this line, remember, this was 2, and this also was -4 to +4. Okay, so that seems to change nothing. Let's see what happens if we do 2,000 points. Obviously, the compute time is a little bit longer, but the plots look basically identical. They look really, really indistinguishable from the previous plots. So the conclusion here, at least from this example, is that changing the x-axis resolution does not change at least the visual appearance of these plots. Now, you can always push this to the extreme. For example, let's try what happens if we set n equals 3. And now we are going to see that, well, this no longer looks like a curve. It's literally just 3 points. And this also doesn't look quite like how it did before. Although the values are still the same. So for the linear function, we still have a value of 2. Okay, so there are always extreme values where this is going to get screwy. And this depends a bit on the nature of the function. You already saw an example of that in the previous chapter. I forget which exercise number it was, but it was the exercise where you plot a function with different resolutions, and we saw that when the resolution was very low, the visual appearance of the plot gave a misleading interpretation about the behavior of the function as x approached 0 because there was this x cubed term in the denominator. Anyway, now what we want to do is basically just get rid of this dx term. Okay, so I'm going to get rid of dx there for function 1 and for function 2. Run this again, and now I went back to 101 sample points between -2 and +2. And here what we see is that the values on the y-axis have changed quite a bit. So remember, this line was at 2, and this was -4 to +4, I believe. And so the function values themselves seem the same. The overall visual appearance of the differences are the same in the sense that the function f1 was just a flat line. It was a constant. And function f2, the differences were this increasing line like this. So the overall visual characteristics are preserved, but the y-axis values are not preserved. Okay, so now that was with 100. Now let's try this with maybe n equals 1,000. So the resolution is now much higher. And again, what we see is that the function itself is not changing, but the function differences are changing. And yeah, also, as I said with the previous resolution, the behavior, so the overall visual appearance of the differences are the same, but the values on the y-axis are different. Now, this should not be so surprising because the delta x term is basically just a scalar. Because delta x is constant across the x-axis, that is to say, the spacing, the gap between each successive x value doesn't change. Therefore, all we're doing here is scaling the function by some number, by a scalar. Now, you are going to learn later that why this is important, including this dx, why we need to have this scaling there in order for eventually this differences, these calculations here, to become the derivative of the function. But that's something to worry about in the future. Here we are with exercise 2 of chapter 3. The goal here is quite simple. This is just giving you a little bit of practice with creating polynomial functions and graphing them in Python. So you want to generate a third order polynomial using 4 random coefficients. Remember that an nth order polynomial has n plus 1 coefficients because we have this term here, x to the power of 0. This is also called the intercept term of the polynomial. Okay, so basically what you want to do is generate 4 numbers at random and then use those as coefficients to create a polynomial of the form y equals some coefficient plus some other coefficient times x plus some other coefficient times x squared, and then the fourth coefficient times x cubed, and then make a plot like this. Now, if you want a little bit of a bonus, you can figure out how to get the plot to look like this in LaTeX. And in particular, what I'm referring to is the fact that this coefficient is negative, but there's no plus sign here. So we have plus, and then, we're summing these two coefficients, or these two terms here, but there's no plus sign. There's just a minus sign because this coefficient was negative. That's actually a little bit tricky to get to work in LaTeX. Other than the LaTeX code, I think you won't find too much difficulty with this exercise. So here I create an x-axis grid. I go from -5 to +5 in 100 steps. That's an arbitrary set of parameters. You can choose whichever other parameters you like. Here's where I pick the random coefficients. So notice there's 4 of them. I'm using the random module in NumPy. And then here's where I'm creating the polynomial. So I say the polynomial y, our outcome variable, it starts off at just being a bunch of zeros. And then I am looping through all of the coefficients and basically saying y equals itself plus the coefficient times x to the power of I, right? So you can see, maybe if I add some spacing here, it's a bit clearer. So we have x to the power of I, and because this is integers incrementing starting from 0, this ends up giving us the powers that we need. And then multiplying by these random coefficients that come from this vector coefs here. Okay, and then here's where I create the name. So this is a string here. It starts here with the $sign for LaTeX math encoding. And then I'm adding, let's see. So this is clear, the coefficient, and I'm just using the first 2 decimal points, and then x to the power of I. So x with I superscripted. And now this funny looking code here, this is actually a 2 characters here in this string, a plus sign and empty. And so then the idea is, depending on the sign of the coefficient, this character either becomes plus sign or just a space. And that is how I solved this part of the exercise. Okay, so we can have a look at this. And yeah, I mean, yours is going to look different from mine because we're picking random coefficients. Every time you run this, it's the same. But what is interesting to remark is that the sign of the cube term is going to determine the long run behavior of the function, which basically means whether it goes from negative to positive, because here's a positive coefficient. And then let's see, we're going to get a negative coefficient eventually. There we go. So now we have a negative coefficient on the x cubed term, and then the function behaves the opposite. So it starts off being large positive values, and then it goes down to being negative. This is a pretty interesting exercise. You are going to implement what's called the Maclaurin series. This is a sum of polynomials. And the idea of summing up all of these polynomials is to estimate a sine wave. Now, it turns out that if you set this parameter here to really be infinity, then you can actually get a sine wave. But we cannot simulate all the way up to infinity. We can't get an infinite number of sine waves in NumPy. And so instead, we are going to estimate this using, for starters, n equals 10. So we're going to have this summation go up to 10 polynomials. But after we sort this out and get this implemented, we are going to explore different values, different ranges of different numbers of polynomials and see how that visually impacts the estimation of a sine wave. Okay, so the goal is basically to create a plot that looks like this. So what are we looking at here? Well, here are the individual dashed lines. You can see a bunch of polynomials. Each one of these polynomials is defined according to this expression. So you're going to need to implement this in Python. The exclamation point is for the factorial operator. Okay, and then you sum all of these up. So the dashed lines show the individual polynomials, and then you sum them all together to create one vector. And that is going to create this black line here, which is, so that's the sum of the first 10 polynomials. And then you can see the blue dots here. I'm showing an actual sine wave that I calculated with numpy.sine. And you can see this looks visually, at least, it looks perfect. So it appears that summing the first 10 components of this Maclaurin series actually gives us a perfect reconstruction of a sine wave. Now, it turns out it's not perfect. We're going to get back to that in the second part of the exercise, but first I will switch to Python and we are going to implement, or I will show you my implementation of this expression here and creating this plot here. So here is the x-axis. I go from minus 2 pi to plus 2 pi. And here I just picked 103 points. You can play around with that as you like. And then here is the variable z. I'm using this variable name z. This is going to be the Maclaurin series. Okay, so then I have a for loop over here. And here is where I implement this equation that I showed. So minus 1 to the power of n times this ratio here. So it was x to the power of 2n plus 1 divided by the factorial of 2n plus 1. Okay, and then, I'm basically plotting the individual function and then summing all of that, the individual polynomials, onto this variable z here. And then I make the plot, and here I have the sine wave. You can see I'm downsampling the sine wave. I'm only plotting every 5 points. And that's just a way to make it a little bit visually cleaner so it's easier to see. So pretty remarkable, I think, that polynomials do not look like sine waves, and yet we just sum up several polynomials and it starts to look like a sine wave. So now for the next part of this exercise, after writing the code, explore different values of the n parameter and also explore different x-axis domains. And what do we make of the visualization? What does that tell us about the Maclaurin series, the summation to infinity, and the relationship between the sum of polynomials and a sine wave? So let me start by changing the number of polynomials in here. So let's make this, how about 3? So here I'm going to add together 3 polynomials. And now what you see is that the sum over these 3 terms in the black line, it still does look visually perfectly like a sine wave, but only in this really restricted domain here, close to 0. And we get further away, after about pi, or a little bit less than pi even. And now, this is basically just the sum of polynomials, and it's driven by this cubic term. So you can see it goes down to minus infinity up to plus infinity, and it doesn't look like a sine wave anymore. Okay, so now let me set this back to 10. And now what I'm going to do is change this range here. So remember, actually, I'll show you this again. This is the original plot, right? So now, again, it looks like the sum of these polynomials is a perfect sine wave. Visually, it appears really, really close. And now I'm going to increase the plotting and calculation domain to 4 pi instead of 2 pi. And now you see something similar to what we saw when I used fewer polynomials. In particular, when we are close to zero, the Maclaurin series, or the partial Maclaurin series, does fit the sine wave really, really well. And then the further away we get, the worse the fit is. In fact, this fit is like terrible once we get out here. Well, what can we do about this? I'm sure you see where this is going. We can increase the order. Let's try 15. So now I'm going to take 15. Oops. Okay, this is starting to get really big. Let's try 12. Okay, well, what's happening is that the factorial function is starting to become numerically unstable. So this is kind of blowing up. But I think you get the idea. Numerical issues in Python aside, the idea is that for any finite value of this summation term here, so any finite number of polynomials, we are only going to be approximating a sine wave, and it's going to look like a sine wave when we're closer to zero and not look like a sine wave as we get further away from zero. So that is why we need an infinite number of polynomials to perfectly define a sine wave. Exercise 4 is pretty straightforward, and it's just a nice opportunity for you to get a little bit more experience with creating and visualizing polynomials. So the goal is to create this plot, which I think looks simple yet elegant. The idea is that each of these is a series of polynomials, so a sequence of polynomials. This is first order, second order, and third order polynomials using coefficients ranging from 0.1 to 2. And then I color coded the lines according to the coefficient magnitude. So you can see that as the coefficient increases, that means going from this line, which is mostly straight, that's the value of 0.1, up to this line here, which has a slope of 0.2 or a coefficient of, 2, not 0.2. You can see that line gets lighter. And same thing here, the lines get lighter, and here the lines get lighter. So not a whole lot of pain points in this exercise. Again, it's just, I like to mix difficult exercises with lighter exercises. So I hope you find that this one is enjoyable and not too challenging. So here I have a for loop where I arrange over values from 0.1 to 2. These are going to be the coefficients. And then I plot x times that coefficient, or by that coefficient times x to the power of 1, or x squared, or x cubed. And then here I set the color to be just a function of the values of I. Okay, and then some plot adjustments here. All right, and then here we see the plot. So I hope you enjoyed this little exercise. Maybe you found that gray lines going from black to light gray are boring, and you want to change the colors or the shapes or the markers or the functions. That is great. What I hope you do in this and most of the other exercises in this book is see this not as a complete product, but as a starting point, a way to inspire you to continue working, continue exploring functions, behaviors, plotting, visualization. And then later on in the book, of course, we will incorporate more difficult math concepts involving differentiation and integration. Using code to explore and experiment with mathematics is an amazing, effective, and also fun way to really learn mathematics. The primary goal of exercise 5 in chapter 3 is to give you an opportunity to continue familiarizing yourself with sim.plot. As I've mentioned multiple times before in this book, in previous exercises, in my other online courses, and so on, sim.plot is really great for quick and dirty plotting. It's not really good for detailed control over all of the aesthetics of a plot. For that, it's better to use matplotlib. Anyway, what you want to do in this exercise is basically create this graph. So you see there's a plot, and you see here's the function in the title, and you want to implement this using symbolic variables, a symbolic function expression, and sim.plot. Let me zoom in here. So we have the function y equals, or f of x equals, x squared minus 2x divided by x squared minus 4. Now, you should already be able to have a quick glance at this function and see that weird things are going to happen when x equals minus 2 and x equals plus 2, because at x equals minus 2 and plus 2, the denominator is 0. Okay, and you see certainly there's something weird going on here in the plot at x equals minus 2. We don't see any, blow up to infinities or anything like that at x equals plus 2. I will talk about that in a moment when I get to Python. One thing I want to mention here is just a little tip for implementing equations and functions that have fractions. Sometimes it's better to have this be defined in Python as two separate variables, one for the numerator and one for the denominator, and then you can combine the two into one function. For simple functions, that's not always necessary, but once the functions get to be more and more complicated, when you have lots and lots of terms in the fraction, then it is often cleaner and safer in the sense of like reducing the risk of errors and bugs in your code to have a separate Python variable for the numerator and for the denominator. And that's what you see here. So I have created two variables, one for the top and the bottom, or the numerator and denominator, and then here I define the function to be the top divided by the bottom. Again, in this like simple little example, it's probably not necessary. You could have just written this all out in one line. But trust me, this approach to defining functions with fractions becomes increasingly useful as you get deeper into mathematics. Okay, so then I use sim.plot. Now there's a couple of extra things here, like this p equals. This is basically a handle, an object pointer to this plot. I use that so I can save the plot as a file, and this is what I use to print the book. If you're not printing to a file, you don't actually need to save this out as an object. Okay, and then, other things you've seen here with specifying the domain, the y-axis, the size of the figure, the title of the figure, and so on. Okay, so now let's have a look at this function and see if we can match what's printed here in the formula with what we see in the graph. So I've already discussed that when x equals minus 2, here we see it goes down to minus infinity, and here it goes up to plus infinity. Now, this vertical line here, this is actually the SymPy plotting engine connecting plus infinity to minus infinity. That is not veridical. That's not what really happens in the function. And so this line is misleading. It really shouldn't be there. But SymPy draws it anyway. In matplotlib, you will also see that line being plotted. But in matplotlib, it's actually easier to adjust the plot to remove this specious line here. Whereas in SymPy, we have less control over that. Okay, so that's one thing to notice. This vertical line is not really in the function. This is just a confusing aspect about how sim.plot is visualizing this function. And then over here, we actually don't see anything particularly interesting happening at x equals 2. In fact, if I just showed you this graph without showing you the function, you would not suspect that anything unusual happens at x equals 2. So what is happening at x equals 2? Well, when x equals 2, then we get basically 0 over 0. And that is a removable discontinuity. So here we have an infinite discontinuity. Here we have a removable discontinuity. In both cases, the denominator is 0, but the difference is here the numerator is 0, and here the numerator is non-zero, so we get these explosions towards plus or minus infinity. Exercise 6 of Chapter 3 is focused on the formula to calculate e, the natural exponential. So this constant that we use as a function, often e to the x. Okay, now I'm going to show you equation 34 in a moment, but the idea is to implement that equation for various parameters, various settings of a parameter that I will show in a moment, and see how that converges to the what I call here the true value of e, with the remark that we are going to actually get the true value using numpy.exp. Now, this is not the true value of E. It is an approximation, but it's much more accurate of an approximation than what we are going to calculate using this equation. So we are going to loosely consider numpy.exp to be the true value of E. Okay, that's the idea. There's two parts to this exercise. I'm going to go through the first part and then come back to the second part. So the first part is to implement that equation that I will show in a moment for various numbers of E, so various parameters. And then you want to print out a table that looks like this. So this is the value of n that we are using. You can think of this like the precision of our accuracy of our estimation. Here we have the estimated value of E. So when we set n to be 1, then E is approximately 2. That's not very accurate, but that's what it is for n equals 1. And then you see for n equals 10, it's getting closer, although, there should be like a 2.7 in there. And then we have the difference to E. So this value here is, so what we see here is like the error. This is the difference, the subtraction from the estimated E to the quote-unquote true value of E that we get from numpy.exp. And of course, what you want is for these numbers to be small. You want these to get closer and closer to 0. So here is equation 34. This is one of the definitions of the natural exponential. There's a few different ways to define it. This is one way. And so here you see the key parameter n. Now, as n, this in theory, to get E exactly, you want to evaluate this expression for n going up to infinity. But we are not going to simulate that. We are going to simulate specific values of n. So in particular, n equals 1, n equals 2, n equals 5, and n equals 10. And that's where this n parameter comes in that I showed you in the table. Okay, so now I will switch to Python, show you the code to implement this, and then I'll come back and explain the second part of this exercise. So the key expression is here. So we have 1 plus 1 divided by I. I'm using that as the looping value for these different values of n to the power of I, or n, in the equation that I showed in the book. And then I'm just printing it out. So n equals this value of the approximating coefficient, then the value of E that we have estimated here, and the difference to numpy.exp. So numpy.exp minus E. Okay, pretty straightforward. You can see that this is really fast, really easy to calculate. And at n equals 10, this is still not a very good estimate, but it is getting better. So the errors are getting smaller from n equals 1 through n equals 10. So that's for implementing the basic algorithm and creating this table. Now for the next part of this exercise, we want to implement this approximation over a range of values of n. So instead of picking particular values 1, 2, 5, and 10, you're going to pick values ranging from 1 up to 1,000. Okay? And then you want to keep calculating these differences exactly like the information that we have in this table, but we don't want to print out 1,000 rows of this table. So therefore, what we are going to do is take all of the data that I'm showing here in this final column of this table and visualize it here. And the idea is to see how quickly this estimation is converging to the very accurate approximation of E that we get from NumPy. And that is what you see in this code here. So we loop from 1 to 1,000, and this ends up just being a lot of numbers, so I'm skipping every 11. Kind of an arbitrary choice, but it just, makes the graph look a little bit nicer, speeds up the computation a little bit. Okay, so you can solve this in a for loop like what I showed in the previous cell. So when we did this here, turns out that because this is just a vector, we can vectorize this whole thing. We don't actually need to use a for loop. Again, if you use a for loop, it's totally fine, but it is not strictly necessary. Okay, so here we get all of the differences, and then I just plot them. So let's have a look at what this looks like. So you see for small values of n, the errors are large, and then the errors quickly plummet down to being, it's hard to tell what this value is here in this plot, but it's very, very small, very close to 0, and the convergence happens quite quickly. Okay, here I have this optional logarithmic scaling. We can uncomment this and redraw the plot. That's just to see what the errors look like as they descend down towards 0 a little bit better. So here on this log plot, you see it's still curved. So it's a supra-logarithmic decrease in accuracy of this algorithm. And that's pretty neat because it's very, very simple to implement, very fast to calculate. The purpose of exercise 7 here in chapter 3 is to explore and further understand the distinction between symbolic numbers and numeric numbers. In particular, we are going to focus on the constant e, so the natural exponential constant e. Okay, and so the idea is to implement this function that you see here. It's a function of beta, and it's e to the beta minus the natural logarithm of beta minus e. Okay, so now the idea is to implement this function as a symbolic expression using symbolic variables in SymPy, but I want you to implement this first e using sim.exp, so that's the symbolic representation of e, and here I want you to use numpy.exp, and this is, as I've mentioned in the chapter and also in previous exercises, this is not the true value of e. This is just a really good approximation of e. Okay, and so then you want to make a plot of this function, and basically just notice that here this is considered e, and this is actually interpreted as some number, right? So this is the approximation of e to like some really good level of precision for basically any real-world application. The coding aspects of this exercise are not terribly difficult. A great opportunity to continue familiarizing yourself with working in SymPy and translating math expressions into Python in general. Okay, so here we see the implementation of this function, and basically what I wanted to point out is the distinction between sim.exp and numpy.exp. Okay, and then the rest is pretty straightforward. We see the difference between this symbolic representation of e versus just the number e. Okay, and now just to illustrate this a little bit more, we can replace numpy.exp with sympy.exp, and then we see here we get the symbolic representation of e. So in this case, with this expression, sympy is representing this as the symbol e, the symbolic representation of the constant e, whereas here, SymPy does not actually recognize this as being e, the constant e. This is just a regular number. That is something to keep in mind as you're working through symbolic calculations. You will see this concept and this distinction between SymPy and NumPy several times throughout this book, and possibly also in your subsequent studies and applications and jobs using mathematics. Here we are with exercise 8 of chapter 3. There's not a whole lot of deep mathematics in this exercise to worry about. This is mostly about gaining more familiarity with coding in math and visualizing, and also with randomly sampling numbers. Now, I don't use a whole lot of random number sampling in this book. It's more relevant for books on like data analysis, statistics, data science, and so on. But there are several cases in calculus and applied calculus where it's interesting to randomly sample from a function to see the distinction between pure mathematics and how math gets implemented on computers and in real-world applications. Okay, so the basic goal of this exercise is to create a plot that looks like this. So here you see 3 functions. These are 3 different log bases. We have log base 2, log base 10, and log base e, which is also called the natural log of x. And the reason why you see these like randomly scattered points here instead of smooth lines being drawn is that the points to evaluate the function on are produced by 80 numbers randomly sampled. So you have to randomly sample numbers between 0.01 and 5, and then make these three scatter plots like this. So the plotting is not so advanced here. It's basically just plotting x by the log of x for log base 2, log base 10, and the natural log, which NumPy just calls log. Okay, and then you can see up here where the x values come from. They are being generated by a uniform distribution between a low value of 0.01 and a high value of 5. And here I specify to use 80 points as the instructions say to do. Okay, and then the fact that I call this 3 different times with 3 different variable names means that the random values of x are going to be different for each of these lines or each of these scatter plots drawn in the graph. Okay, so you can see looks like this. And it's also interesting to see the difference between the different log bases. They all look really similar. All the log bases, or all the logs, behave in very similar ways. It's just that the slope is different depending on the base of the function. Exercise 9 is focused on piecewise functions, in particular, implementing piecewise functions in NumPy and visualizing them in Matplotlib. Okay, so here is the function. Here you see there are 3 pieces to this function. It equals 0 for negative values of x, minus 2x between 0 and 3, and x cubed divided by 10 when x is greater than or equal to 3. Okay, so you want to create 2 sets of variables for representing this piecewise function. One variable, is a single NumPy array, so one variable that contains all 3 pieces. So this is going to be one vector for x ranging from -3 to +5. Okay, that is one implementation of this piecewise function. A second implementation of this piecewise function is going to involve 3 separate pieces. You can make these 3 separate variables, or maybe you want to have these as 3 separate items in a Python list data type. I will let you choose, but you want to basically separate these 3 pieces of the piecewise function into distinct Python objects, distinct variables, or distinct components of a variable, as opposed to a single vector, a single array that you would get for the first part. Okay, so once you have those 2 representations of this piecewise function, you want to then visualize both of these in Matplotlib. So here we see the visualization of this function as one vector when this is represented as one NumPy array. And over here we have the plotting where we have one separate vector, so one separate Python variable for each piece of the piecewise function. Okay, I'm going to have more to say about how this looks and which one is correct, which one is less correct, which one is misleading, and so on. But I will have that discussion when I switch to Python. Here I'm defining the grid spacing for, or the grid values for the function to evaluate the function on. So I have x going from -3 to +5 in 100 steps. And now here is approach 1. So I said we need 2 different approaches for representing this piecewise function. First, we get one array, one NumPy variable that corresponds to all of the function values for all the pieces. And the way that I implement this is by defining each of these pieces multiplied. So the description of the function, the definition of the function piece, multiplied by a Boolean vector that tells us where we are relative to x. So this is going to be a Boolean vector that is true for all negative values of x and false for all positive or non-negative values of x. And that vector of trues and falses gets multiplied by 0. So that corresponds to piece 1. And now here we have -2x, and that gets multiplied by this Boolean vector that is true for all values of x between 0 and 3, and it's false for all negative values of x and values of x equal to or greater than 3. So that is piece 2. And so on for piece 3. So the idea is that each one of these pieces is equally long as x. but they are, each of these pieces is 0 for outside of its little subdomain and some non-zero value, or at least the possibility of a non-zero value, inside the specified domain. Okay, then I can just add them all up together. So that's the logic of creating the piecewise function as one NumPy array. Okay, and then I plot it, just x by y, very simple. Okay, and then here is approach 2. I'm plotting each piece of this piecewise function separately. So now you see I have 3 plotting functions. I'm calling plt.plot 3 times, once for piece 1, and then again for piece 2. And this should look familiar, right? Because this is the same thing as what I have up here. So you can see I'm plotting each of these function pieces separately. Okay, and then that gives us this plot. Okay, so what do we make of this? Well, what we can make of this is that this line here is incorrect, right? This is misleading. It looks like the function just goes smoothly as a straight line from, just below x equals 3 to just above x equals 3 to, whatever these values are, -5 up to whatever this thing is. That is not the case. That looks like the case visually. That's how the plot looks, but that is misleading. So to be clear, this straight line here is correct. This straight line here is correct. This curved line here is correct. What is incorrect in this plot is this line right here. The function actually jumps instantaneously from this point to this point with no intermediate value. So this is wrong. Okay, and then we have this plot over here where we plot it with 3 separate pieces. And this is a little bit more accurate. This is a better depiction of what's happening in this piecewise function. We see the individual pieces, and there's nothing in between because there are no function values between y equals 3 over here and y equals whatever this value was. Now, on the other hand, I would like to stress that this is purely about visualization. So the actual vector y, that is the single vector that I created, this is correct. There's no errors in this actual variable. So Python is representing the piecewise function accurately. The problem is with the visualization. And the problem there is just that, Matplotlib wants to draw a straight line between these points. Okay, so that is something to be aware of. I'm going to show you later how to remedy this situation so that we can have piecewise functions represented with one variable and still visually correctly displayed. This exercise is a close follow-up to the previous exercise. So make sure you've solved exercise 9 in chapter 3 before doing this one. Okay, so the main idea is basically just to re-implement the piecewise function in the previous exercise, but this time in SymPy using the function sim.piecewise, and then visualize using sim.plot. And the question is whether the misleading line, the spurious line that we observed in Matplotlib is also present in SymPy. And spoiler alert, the answer is yes, the problem still exists. Again, this is just about visualization. SymPy is not actually representing numerical function values between these 2 points, but this is how the SymPy plotting engine is designed. So here we are in SymPy. I'm importing a symbolic variable x, and here I list the 3 pieces of the function, and then here I put them together. So sim.piecewise, and then we have tuples for each of the pieces. So in this case, there happens to be 3 pieces to this function, so we need 3 tuples. And within each tuple, you have 2 elements of each tuple, and that is the definition of the function, and then the restricted domain for that function. So piece 1 simply equals 0, and that is the case whenever x is less than 0, and so on. So this is the same function from the previous exercise. And then here I'm using sim.plot to plot this function with a couple of additional specified options. Again, you don't need to request an output of sim.plot unless you want to do other things with that plot, like have multiple plots, multiple subplots, or if you want to save it like this. Otherwise, you can just have a call to sim.plot like that. Okay. And so the main point of this exercise is, well, 2 points. One is to give you some more experience working with SymPy and in particular creating piecewise functions in SymPy, but also to see that the SymPy plotting engine is still incorrectly including a line here. Again, I said this in the video for the previous exercise, but it's a very important point. This piece here is correct. This piece here is correct. This curvy piece up here is correct. What is incorrect, what is misleading in this plot is this straight line here. This does not actually exist in the function definition. Now, why sim.plot, or I should say the SymPy developers, don't add a little fix to stop this line from being drawn for piecewise functions, I cannot say. SymPy is an amazing library. It's imperfect. It does some weird things, as you will discover throughout the rest of this book. This and the next several exercises are focused on discontinuities, how to implement discontinuities in NumPy and SymPy, and also how to visualize them properly in Matplotlib. Okay, so first for exercise 11, we are going to begin by implementing this piecewise function in NumPy and then visualizing it in Matplotlib. Now, you'll remember from the previous couple of exercises, and also I discussed this earlier in the chapter, that just using Matplotlib can lead to misleading conclusions about piecewise functions, particularly if there are discontinuities and jump discontinuities or removable discontinuities. So what you want to do here is make sure that your plot looks like this. You can see here is the first piece. So this is just some sine function for negative values of x. And here, the third piece over here is just some, x squared, basically shifted version of x squared minus x squared for positive values of x. And then at exactly x equals 0, we have the value of 1.5. So this is a jump discontinuity. And importantly, what you do not see, which you did see in the previous couple of exercises, is misleading lines here, suggesting that the function actually has values between this point and this point, and between this point and this point. It's not in the function definition, and now it's not in the plot. So basically, you want to figure out a way to plot this function appropriately. There are several correct ways that you can implement this exercise and solve this exercise. I'm going to show you the way that I chose to do it. Again, that's, there's multiple ways to do it. Okay, so the way I set this up is to have this variable called pieces, which is actually a Python list. This is a list with 3 elements, and each element is itself a vector corresponding to each piece of this 3-piece function. So I have this list for the different pieces, the function definitions, and then I have this other list here called xDomains for the subdomains or restricted domains of each piece of this function. And then I plot. Now here you can see I'm plotting in a for loop because we have 3 pieces, so we need 3 different calls to plt.plot. Okay, and the important thing here, the critical thing here, is that I'm using separate markers for each of the pieces. So this is the marker for piece 1, which is going to be a line. This is the piece for part 2, which is literally just one dot. It's just one point at 1.5 where x equals 0. And then we have this marker for the third piece, which is also a line. Okay, so I hope that makes sense. There are, as I said, there's several correct ways you can plot this, but the point is that no matter what you do, you're going to need to cut up the function into separate pieces somehow, and then plot each piece differently. So this is one way to solve it. Exercise 12 here follows up from the previous exercise. Essentially, what you want to do is just re-implement the piecewise function from exercise 11. That's what I'm showing here. But now, instead of doing this in NumPy, that was the previous exercise, in this exercise, you want to implement this in SymPy. And then create a plot of this piecewise function using sim.plot. Now, this is just a bit of a refresher about using SymPy and creating piecewise functions in SymPy, but there is one little tricky, subtle point about SymPy that you are going to discover when you implement this expression here. After having gone through this chapter and also the a few exercises ago where we implemented piecewise functions in SymPy, there isn't really much in this exercise here, exercise 12, that is new or really different. You can see I'm using sim.piecewise, and I'm implementing each of the pieces as a separate tuple, where the first element of the tuple is the definition of the function for that piece. And then the second element is the domain restriction for that particular piece. Okay, and then we use sim.plot to visualize it. I'm going to talk about this line in a moment. So first to visualize, and what you see is that sim.plot is actually plotting this incorrectly, right? So we had, let me go back up to this plot here. This is what we created in NumPy and Matplotlib. And remember, what I did here was plot each of these three pieces of this piecewise function separately. So I carefully customized the code to make sure that this function was being correctly, accurately displayed. In contrast, SymPy is, we don't get any error messages when creating this, so it correctly understands the piecewise function, but sim.plot is not drawing this correctly, at least just from a basic sim.plot call. Now, again, as I've mentioned several times before, if you really want to use sim.plot, SymPy's plotting engine, you can go through and, make three different calls to sim.plot into the same axis and plot all of these function pieces correctly and accurately. But if you want to do that, then go for it. I've seen people do that. It's fine. It's possible. It's not so difficult. In my humble opinion, it's generally always better to translate this function into NumPy and then use Matplotlib to make a more easily customizable plot like this. Okay, the last thing I want to discuss in this video is this thing right here. So here I'm using sim.eq, which stands for equal. And basically, the way that this function works is you provide two inputs, and SymPy will just determine whether these two are equal or unequal. If they're equal, then the result is true, and if they are unequal, then the result is false. Okay, so the issue is that we cannot simply write x equals 0. This expression is sensible, and it can work sometimes for NumPy, but SymPy doesn't correctly work with this. Now, that's not obvious from just looking at the code and running the code. But if we were to evaluate this function, see what this function looks like, we see that fx, that's the variable I created, it has two pieces for x less than 0 and x greater than 0. But here, SymPy is not telling us what is the value of this function at x equals exactly 0. So is the function equal to 0, or is it equal to pi squared, or is it equal to 100 quadrillion? We have no idea. We don't have any information about what happens when x equals 0. It's simply missing. Okay, but if we were to go back here and use this built-in SymPy expression for testing equality, now I'm going to rerun this code here, and then we can look at the function again, and now we see that there are three pieces. So now SymPy has correctly identified what happens at x equals 0, and the function has a value of 1.5 as we specified here. So this is something to keep in mind when you are implementing piecewise functions and discontinuities. Exercise 13 continues along our trajectory of learning how to represent piecewise functions and discontinuities in NumPy and how to plot them accurately using Matplotlib. Okay, here we have a removable discontinuity. So here is the piecewise function. You can see it is a sine plus a quadratic for basically all values of x except for x equals exactly 0. And when x equals 0, the function takes on the value of pi. Okay, so here's what that function looks like. Notice that there is no connecting line here going from the piece 1 of the function to piece 2 of the function and then back. So this piecewise function and this removable discontinuity is accurately visually depicted using the code that I wrote. Okay, as I've mentioned multiple times before, there are several correct ways to solve this exercise. I'm going to show you my solution, but any solution that you came up with is great. If it looks different from mine, that's great. As long as you have solved this problem correctly, then you should be happy and I will be happy. So here is how I chose to implement this piecewise function. You can see, so here I create the vector of x values. Here is where I define the function. Now, this is piece one of the function, but it spans all of the x values. So this function here, just this one line of code, is not entirely correct, but it's very close to being correct. And then what I do is find the function value where x equals 0 and replace that value, whatever it happens to be from this line of code. I replace that one data point with the value of pi, or at least numpy's approximation of pi. I will get back to this little bit of code in a moment. First, I want to show you the plot. Okay, so then, so now over the past several exercises, I've shown you multiple different ways of accurately visualizing piecewise functions. And here what I chose to do is basically make a scatter plot. So you can see I'm drawing dots, little circles here instead of lines. If I would have just specified it to draw a black line like this, then we actually would have this incorrect representation. This is misleading here because this straight line coming up and the straight line coming down, this is not really in the function. That's a misrepresentation in matplotlib. But when we plot it with a marker and no line, then we get the correct visual representation. Now you can also see, you can see some individual dots here. You can also try to, let's see, if we make the resolution lower, it's going to be more obvious that these are individual dots and not a line. And if you increase it, let's do 1,000 points. Now it's going to look much more like a line. Again, we're not really changing the function definition. We are changing the resolution for the function to be visualized. Okay, let me go back to whatever this was initially. Okay, so that's all great. Last thing I want to mention in this video is just a little bit about this line. Now you might think that it should be something like this, where x equals 0. The issue here is that this is an extremely precise data value. If we say, equals 0, then we don't know whether this vector of x is going to contain exactly the value of 0. Now it turns out that we can guarantee that it will contain exactly 0. That will happen if you have the vector go from minus some value to plus some value with an odd number of points. I've discussed that earlier. I forget if it was earlier in this chapter or in the previous chapter, but I have discussed how to guarantee that the value of exactly 0 is really in the function. But let's say, the function piece was for 1 or some other number. We don't necessarily know, or we don't want to assume that the value of exactly 1, like 1.00000 like this, is going to be inside this x vector. So instead, we allow a little bit of tolerance. And so what we say is we want the value that is closest to 0. Maybe it is exactly 0, maybe it's a tiny, tiny bit different from 0, but it's the closest numerical value in this vector to our desired value of 0. And that's what this code does. It basically takes the absolute value of our x vector minus the value that we're looking for. In this case, it's 0, but I just wrote in the code just so you can see, we can change it to look for value of 1. And then basically it rectifies that vector and finds the minimum value, which is the smallest value in this absolute vector. Okay, so I'll plot this again just so you can see what it looks like for when I change that from 0 to 1. So now we have the discontinuity at x equals 1 instead of x equals 0. Welcome to exercise pi, exercise 3.14. So here we have infinite discontinuity. So what you want to do is implement this function here to create this plot here. Now I want you to use 1001 points linearly spaced between x equals -2 and x equals +2. And I've also drawn in these gray vertical dashed lines. These lines here are not part of the function definition. Instead, these are just visual guides to help us see that there are important things happening in the function at x equals -1 and x equals +1 that you see obviously from the definition of the function. When x equals -1 or +1, the denominator is 0. And so weird things are going to happen around there. And whether we go to -infinity or +infinity depends on the value of x relative to 1. So if x is not exactly equal to 1, but a tiny, tiny bit smaller than 1, then the denominator is going to be a very, very small positive number, versus when x squared ends up being a number that is not exactly equal to 1, but very, very close to 1, but just a tiny, tiny bit larger than 1, then this is going to be a negative number, because this will be a little bit bigger than this. So we get negative infinity here. Okay, anyway, once you visualize this, once you've implemented this in NumPy and created this plot in Matplotlib, then observation, you are going to get a warning message about divide by 0. So the question is, why do you get that warning? What is causing that warning message? Which value of the function produces that warning message? And what happens when you use 1,000 x-axis points instead of 1,001, right? So this plot is created with 1,001 points. So try using 1,000 points and see what happens. Here I have the function definition for 1,001 x-axis points between -2 and +2. Okay, here I plot the function, very straightforward. Here I plot the two vertical dashed lines, also pretty straightforward. Okay, so in terms of coding, there's not a whole lot of difficulties involved in this exercise. This is a little bit more about conceptual points of implementing math on digital computers with finite precision. Okay, so the function looks great. This plot looks like what I show in the book. Okay, here we get this error message. Now, I'm sure you figured it out. We get this message divide by 0, obviously because we are dividing by 0, when x equals exactly 0. Okay, now we are going to try changing this function. Instead of being 1,001 points, it's 1,000 points. And now, notice two things have changed. One, we no longer see that warning message. And two, we now see this black line in this function. So you see the gray dashed lines. In fact, I'll even comment this out. So you see these misleading black vertical lines. This is a theme that you've seen many times already in the past exercises and also earlier in this chapter. Okay, so why does the behavior change when we went from 1,001 points to 1,000 points? Here's the reason. The reason is that when we have an odd number of points between a minus some value and plus that same value, then we get an exact 0 right in the middle. And that means that now with an odd number of points, there is one value of x that is exactly equal to 0. And so therefore we get the warning message, and the function value at those points is nan. So when x equals exactly 0, we get a value of nan. And that's actually, I can show you that right here by replacing xx with exactly 0, and we get 3. I'm sorry, I meant 1. Here we get division by 0, and the answer is just undefined. Okay, so that value of nan actually is a missing point in the plot. And so now Matplotlib is going to correctly display this function by not including this line here because there is an nan value. Okay, and let's see, but then, when I set this back to some even number, it doesn't have to be 1,000. It can be any even number. Now we get values that are very close to 0, but not exactly 0. And therefore, we get this line here because all the points in the function are valid numeric finite numbers. And so Matplotlib draws a vertical line between these 2 points, or a near vertical line. So I hope you found this demo interesting. Let me undo all of these things. The last thing I want to mention, let me go back to even, is another way to correctly visualize functions that have these kinds of discontinuities. So piecewise functions or functions with infinite discontinuities like this is actually just to replace one of these values with an NaN. So we can say fx where x equals -1 equals numpy.nan. Now, I mentioned in the previous video and also earlier in the chapter that this is not a good strategy. You want to incorporate a bit of code like this here, but we can, yeah, so there's a little more coding that's involved here. But the basic idea is that you can also manually override this function value at the x-axis value closest to, this would be xx, closest to the point of the discontinuity. You can just manually specify that to be NaN, and then you are still going to get a graph that looks like this with an even number of plots here, like that. The goal of exercise 15 is for you to discover a SymPy utility that allows you to identify domains, domain restrictions, and singularities. Now, singularity is not a term that I have been using a lot in this book, but basically it's a point with an infinite discontinuity. That is a singularity of an equation. So what you want to do is fairly straightforward. Implement equation 3.104. That's just from the previous exercise. So it's this equation, 3 over 1 minus x squared. That's what we implemented and explored in exercise 14. So implement that equation in SymPy as a symbolic expression, and then use the function continuous underscore domain. That's the name of a function in SymPy to find the domain of this function. And then you want to identify where this function has infinite discontinuities. I won't tell you which function to use, but there's a hint embedded somewhere in this paragraph is a hint about how to identify in SymPy x values where a function has infinite discontinuities. You can see there's not a whole lot of code that's involved in this exercise. It's basically just finding the right function and the location of the function, and then figuring out how to call it. So here is the symbolic implementation of the function from the previous exercise. So 3 over 1 minus x squared. And here I'm using the function continuous domain, which is contained inside the module sim.calculus.util for utilities. Okay, and then you provide 3 inputs into this function. The variable name of the expression, which is here, the variable itself, which is x, but maybe in other cases it'll be y or tau or whatever is the variable that you're working with. And then you need to specify some interval to calculate the domain of continuity within. So I'm using here an interval of -2 to +2 because that's what I specified from the previous exercise. Okay, so now basically SymPy is telling us that this function is continuous in the domains -2 to -1, -1 to +1, and +1 to +2. Now, if you want to look at all of the entire interval, so from -infinity to +infinity, you can use sim.s.reals like this, and make sure this is a capital R. Okay, and then we're going to get calculating an interval based on the entire real number line. So this looks almost the same as the previous result, but now we're going out to -infinity and to +infinity based on this interval instead of this specified subdomain interval. Okay, and then the singularities in SymPy, this is straightforward. Once you figure out that the function name is singularities, you just input the function and the variable. And yeah, SymPy returns that this function has singularities or infinite discontinuities at x equals -1 and x equals +1. Exercise 16 is focused on oscillating discontinuities. So in particular, you will see an example of an oscillating discontinuity. implement this in NumPy and then visualize it in Matplotlib. Okay, so here is the function. It's the sine of 1 over theta minus 1. Now you can already see from looking at this function definition that some wonky things are going to happen as theta, the variable here, approaches 1. Okay, so as theta gets closer and closer to 1, either a little bit below 1, like 0.99999, or just above 1, like 1.00001, then this fraction here is going to blow up to plus or minus infinity, depending on the sign here. And then we take the sine of this, and basically that's going to spin this sine wave faster and faster. So the frequency of the sine wave is going to increase. And that's our function. So implement this expression in NumPy, and then draw it using Matplotlib for theta ranging from -1 to 2. Now you can see, here's where it gets wonky here around theta equals 1. Now it kind of looks like it's getting choppy and the values are getting smaller. I'm going to have more to say about that when I switch to Python in a moment, but basically this is just a discretization error. The code here is fairly straightforward. Here I define this variable xx, although I called it theta in the book. So we go from -1 to 2 in 1001 steps. Of course, this resolution is kind of arbitrary. You can play around with this parameter as you like. Here's the definition of the function, and then we just plot it. Pretty straightforward. I called this function O for oscillating discontinuity. Okay, so very nice. Now what I would like to do is basically explore the reason why this function appears to be choppy, and it looks like the values get smaller and larger and smaller, and they do kind of weird things. Basically, the problem here is that the function is changing faster than our discretization rate. So we can fix this or improve the visualization in a couple of ways. One way is to increase the resolution here. So now I have 10,000 points instead of 1 point. And I think I'll make this line width maybe 0.6. How about that? So I'm just making the line a little bit thinner. Okay, so now you see that this is getting compressed. Okay, we can investigate this even more by specifying the x-axis limits. So how about instead of specifying it to go from the first to the last point of x, or theta according to the formula in the book, how about we say 0.9 to 1.1? Okay, so now all I'm doing here is zooming in to this range here. So we're getting closer and closer to 1. And now you see it's even more clear here that the function is increasing in frequency as we get closer to 1. Actually, I think now that I'm working through this, I think a better way to do this is to leave this x-axis limit here, but then change this instead. So let's set this to be, instead of from -1 to +2, let's go from 0.9 to 1. So basically this is keeping the resolution equally high. Yeah, this looks much nicer. Okay, so now we can zoom in even more. We can say 0.99 to 0.01, and this is really, we are really zooming in here. You can see that we're starting to run into some numerical issues here as we get to 1. In particular, when we get to exactly a value of 1, then of course we have 1 divided by 0. So we're going to run into some numerical problems here. Nonetheless, I think you see the idea of an oscillating discontinuity. This function is spinning up faster and faster and faster. It never actually settles on a particular value, which means there is no limit. More specifically, the limit is not a finite number as we approach theta equals 1. Exercise 17, and also the next several exercises, are focused on composite functions. Mostly, the goal here is to increase your familiarity, your experience levels, working with composite functions, and also thinking about composite functions and this principle of commutativity, which means if f of g of x equals g of f of x. So whether you can embed these functions inside each other both ways around. Okay, so in this exercise, 17, what you want to do is implement these two functions, f of x and g of x, in NumPy, and then you want to plot both of these functions using Matplotlib. So the two functions, and then their two orders of composition, so f of g of x and g of f of x. I will have a couple of remarks about what this plot reveals about these two functions, and I will discuss that after showing the code. As is often the case in math coding, there are multiple correct ways that you can solve this exercise. Nonetheless, when it comes to making composite functions, it's generally almost always going to be a good idea to implement these functions as Python functions, either standard, normal Python functions with def keyword, or as Lambda expressions, because that's going to facilitate making composite functions like this. Okay, so here I use standard Python functions to create function f of x and function g of x. And here you can see I'm creating the composite functions. Now, what's neat about creating these math functions as Python functions with regards to making compositions is that the Python code actually looks basically the same as the math implementation, the math formulas. So f of x of g of x and g of x of f of x. Okay, and then I plot f and g and the two orders of composition. Oops, I have to run this code first. There we go. Now we can see the figure. Okay, and the main point to see here is that the dashed line, so that's this one, that's f of g, and the dots, the gray dots, that's this one, that's g of f, those are not the same. Those are distinct functions, and that means that these two functions, f of x and g of x, do not commute. They are not commutative. As I explained earlier in this chapter, there are functions that will commute with each other. So there are special cases. There are pairs of functions for which f of g of x equals g of f of x. In that case, you would see that the dots and the dashed line would overlap perfectly. That's not the case here because in general, there are exceptions, but in general, any two randomly selected functions are not going to commute with each other. Exercise 18 continues with exploring function compositions in Python. In this case, we are going to have three individual functions, f and g and h, and explore two different triple compositions. So g is embedded inside h, which in turn is embedded inside f. So we have f of h of g, it gets confusing to read. And we have f of g of h of x. Okay, so all of that is going to produce this figure that looks like this. I have a couple of questions that I would like to ask you to continue exploring. I will get to that when I show the Python code. So here I have encouraged you to implement these functions not as regular Python functions using the keyword def, as I did in the previous exercise, but as Lambda expressions. There's no particular reason why you should prefer Lambda expressions for this exercise and regular Python functions for the previous exercise. I'm just giving you these different recommendations for different styles and different approaches in coding to make sure that you are familiar with these different mechanisms and different coding approaches. Okay, anyway, so here is our three individual functions, and here is the two composite functions. So f of g of h and f of h of g. All right, pretty straightforward, although there's a lot of letters, so, it's just a lot to keep in mind here. Okay, so, and then plot those. That part is pretty straightforward. Now, I have a couple of questions for you. One question is, why do we get these warning messages here, divide by 0, and invalid value? Obviously, you get some hints here because you see that it's a problem with the log function. Here, again, a problem with the log function. And here, it's a problem with the sine function. Okay, and then a related question, very much related, it's actually basically the same answer, is why do we get this second composition, so f of g of h of x, why does that go to negative values? We can see negative values here, but for f of h of g, we don't see any negative values. There's no values less than 0. That might seem a little confusing at first because they all come from the three same functions, right? It's all from these three functions. And in both cases, f is on the outside, is the final function that wraps around these other two functions. Well, to understand the answer to this, and I will let you ponder this in more detail, basically you just have to think about which values can be negative and positive when we embed g into h versus h into g. And it all has to do with where this log is placed and the fact that x here is squared. So in other words, the output of h can never be negative, which is good because we do not want to have any negative values inputting into the natural logarithm. Okay, so that's the answer to that question. And the next thing I have here is a little bit of a challenge for you. I don't specifically show the answer, but I would like you to come up with another composition. So take these same three base functions, f, g, and h, and then compose them in a different way that also allows the domain of the entire composite function to be all the real numbers, right? So that's what you see here. We can have negative numbers and positive numbers. Here we can only have positive numbers. And I would like you to come up with another way of composing these three functions in order to have a composite function that can also take negative values for x. Exercise 19 follows up on exercise 17. So in exercise 17, we saw that when we took two functions and we composed them in two different ways, they did not commute. That was f of g of x and g of f of x. And when we plotted those two on top of each other, maybe I'll scroll back up to that plot, we saw that they are not the same. These two functions, or these two orders of composing these functions were not the same. They give us distinct results. So these two functions do not commute with each other. But now we are going to explore whether these two functions commute with each other. So the natural log of 2x and each the x divided by 2. So here I call these p of q and, p of x and q of x. So use regular Python functions, so using the def keyword, to implement these two functions and then plot the functions individually and both ways of composing these two functions, so p of q of x and q of p of x. I will have more to say about interpreting this graph, and I'll discuss that in after showing the Python code. So here are the two functions, the two Python functions for implementing these math functions. You can see it's a standard Python function. It's only on one line of code, but that's because, normally, you're used to seeing functions look like this with the function definition and the output on a separate line. In general, it's not necessarily such a great idea to have the function in one line of code, but just because it gets, visually cluttered. But in this case, the function definitions are so simple that there's really no problem with having this be one line of code. Okay, and again, there's no particular reason why this needs to be in a function. You can also just write out the compositions, but I chose to do it this way, just to give you some more practice writing Python functions. Okay, so anyway, here I'm plotting p of x, q of x, p of q of x, and q of p of x. And here I'm just downsampling the results to show only every 10th data point, and that's purely for ease of visual inspection. It just makes the plot a little bit easier to interpret. Okay, so here we see, let's start with this one. So here we have the natural log of 2x, and it looks like the natural log of any number. You can see, normally as we approach 0, this plummets down to minus infinity, but here it just kind of gets small because looks like I start at 0.1 here. So if you want to see this go even further, you could plot this at 0.01. Oh, I guess I also specify the y-axis limits here. Let me see. Comment this out. You can see I'm just enjoying playing around with my own code. This is now the e to the x is blowing up here. Of course, I encourage you, as I mentioned many times before, I encourage you not to, just look at my code and run it and walk away, but instead to spend a lot of time exploring and playing around with this code The code files that I write are basically your way of exploring mathematics empirically. Okay, that meta comment aside. Right, so where are we again? Yeah, so here we see the logarithm of x. And then here in the gray line, we see e to the x divided by 2. So it's just e to the x with a scalar. And then here we see the two function compositions. So p of q of x and q of p of x. Now, what you see here, which is very different from the previous example 2 exercises ago, here you see that the dots and the dashed line appear to overlap perfectly. Now, we need to be very clear about this, that you shouldn't look at a graph like this and make really important claims about mathematics just from visual inspection of a graph. But it certainly looks like these two functions commute with each other. So that is to say that p of q of x equals q of p of x. In fact, that really is the case here because these are inverses of each other. And when one function is an inverse of the other function, then those two functions will commute. That's one of the exceptions for the rule of commutativity and composition. Okay, so natural log of 2x is the inverse of e to the x divided by 2, at least within a restricted domain. I'll talk about that another time. Now, where do we get this 2 from? Well, to understand why we have a 2 inside the natural log and dividing by 2 in the natural exponential, you need to understand a little bit more about derivatives and differentiating functions. So we can hold off on that until a few more chapters. But for now, suffice it to say that if you have some scalar multiple inside the natural log, if you want the inverse of this function, that's e to the x, but then you need to divide by that same scalar. And if that seems weird or mysterious, then that's great because you have something to look forward to learning about. You will understand exactly why that's the case in a few chapters from now. So far, all of the function composition exercises in this chapter involved using NumPy and Matplotlib. And so the goal of exercise 20 is to introduce you to creating composite functions in SymPy. Now, there's a couple of ways that you can do this, but I recommend using the substitution method on a SymPy object. Okay, so you already know how to substitute a number for a variable using the subs method in SymPy. And this would be a way to evaluate a function for a particular value of x. So now it turns out you're going to do the same thing, but instead of substituting a number, you're going to substitute a mathematical function, which is represented as a SymPy object, a SymPy expression. Okay, so here is what you want to do. In SymPy, implement these three functions as three separate variables or three separate SymPy expression objects. F of x is sine of x, g of x is the natural log of x, and h of x is 2x squared plus 5. And then you can make these two visualizations of these compositions. Now, you can either do this as separate SymPy plots, or if you want, you can figure out how to make a subplot geometry in SymPy to put this into one figure with two different axes. All right, either one of those methods is fine. Now, I didn't write out the letters here for composition, so you just have to look at the titles. Maybe let me zoom in here a little bit to know what the function order is. Okay, so here in panel A, we have y equals f of g of h, and over here in panel B, we have y equals g of f of h. Okay, very nice. Now I will switch to Python and show you how to make composite functions in SymPy. So we start by creating a symbolic variable. The variable is x. It's internally represented as x, but I am giving it the variable name sx. The s is for symbolic. So this is potentially a little bit confusing about SymPy, but basically this is what the variable will look like when SymPy prints out any expressions, and this is how we refer to that symbolic variable when writing code. Okay, so here we have f and g of h, these three functions. Pretty straightforward. You just have to be mindful that you're using sim.sign, for example, and not numpy.sign. And here is how we use the substitution method. Okay, so it's a little bit complicated when you first look at it. So let's just walk through it piece by piece, starting from the innermost part of this code. So we take g of x and we substitute wherever we see x, we replace it with h of x. So this expression over here, this function over here. Now, this is, in terms of syntax, this is no different from what you've seen earlier in this chapter and what you will see elsewhere. So, if you want to evaluate the function g of x for x equals 3, then this is how you do it. So all we're doing here is substituting this expression for wherever we see x in g of x in here in the log. Okay, and then, so that is, the innermost composition, and now we need to embed that composition into another function. And that's what I'm doing here. So I say f of x dot subs. So now we have, wherever we see the variable x in f of x, we replace that with g of x, which itself already has x replaced with h of x. I hope that makes sense. You can walk through this carefully and see that just using the substitution method to embed one function inside x for another function, and that all gets embedded inside x for another function. And here I also have these two different formats for substitution, with a dictionary where I specify key value pairs, so the variable name and what I want to substitute. And here I'm using this other optional method where I say the variable name and then the thing that I'm substituting for. There's no reason why it has to be one format and then the dictionary format here. I'm just writing it in these two ways to remind you of these two different approaches for using the subs method. All right, all that said, okay, so now we create the two plots. And now the key to making a subplot grid in SymPy plotting engine is to create two separate outputs for the two plots. And then you can say show equals false. So we are not actually showing these plots here when I create them. Instead, I'm just storing the plot handle in this variable P1 and P2. And then here I create the actual figure, saying with plot grid, and now here we have a 1x2 geometry. These are the two plot handles, and this is the figure size. Okay. Here I'm saying show equals false just because it's going to be shown here when I write p.save. Oof. Okay, so mathematically, this is not a terribly complicated exercise, but in terms of SymPy, I hope you feel that you have increased your knowledge, your skills of using SymPy to represent, work with, manipulate, and visualize functions. The goal of exercise 21 in chapter 3 is to learn how to use SymPy to calculate the inverse of a function. In particular, you are going to use the method sim.solve, so the function solve in SymPy. There's other related functions like solve set and so on, but for this application, we only need this one method, sim.solve. Okay, so how do you use sim.solve? Well, you're going to have to figure that out a little bit on your own, but I will give you a hint. The hint is that you need to rewrite the equation to equal 0. So for example, if you want to solve for x in the equation 4x equals 2, then what you actually input into sim.solve is not 4x equals 2, but 4x minus 2. And then implicitly, this equation is set to 0. So in SymPy, you don't actually need to write equals 0. You write 4x minus 2, and sim.solve will assume that it's that you're trying to solve for x in this expression equal to 0. Okay, so that's just a very brief intro to sim.solve. So with that in mind, what you want to do is use SymPy to find the inverse of this function. Very simple little function, 2x plus 3. Okay, so how do you find the function inverse of that function using sim.solve. That is what you need to discover. And then to confirm the accuracy of your answer, what you want to do is use the subs method to show that the composition of the function and its inverse gives back x. So that is the definition of the function inverse. You can see that written out two ways here. So they are commutative, the function and the function inverse. So f of f inverse of x equals x, and f inverse of f equals x. Okay, so you know how to create these composite functions in SymPy from the previous exercise. Okay, so all of that. And then the last part of this exercise is basically to repeat this exercise, rerun the code you've written, but just change the function a tiny bit. So now we have the function g of x equals 2x plus the sine of x. So instead of adding a constant, we're adding another function, and it's a sine. Make sure you use the symbolic sign and not numpy.sign. And then the question is, what happens and what does it mean? So, we want to know, can SymPy find the inverse of this function? So here I have a little bit of code. This just demonstrates how to use sim.solve in the little example equation that I showed in the book. So the equation was 4x equals 2, but as I wrote in the book, what we need to actually input into sim.solve is this expression, or this equation re-expressed being equal to 0. So obviously the way to do that is just subtract 2 from both sides. So we end up with 4x minus 2, and I'm not actually writing equals 0. That is implicit in this expression. By the way, this variable sx is a symbolic variable for x I created in the previous exercise. Okay, so then we can just solve. So we write in the expression we want to solve for, and then the variable that we want to solve. You need to specify the variable in cases where there are multiple symbolic variables, as you will soon see. Okay, and then SymPy tells us that the solution, so x, solves this equation when x equals 1/2. And that's also obvious from looking at this expression here. Okay, very nice. That was just a quick demo to sim.solve. Now for this exercise, now we need to have a symbolic variable y. So the function was 2x plus 3, so that's over here. That was the right-hand side of the function. The left-hand side of the function was f of x, and here I'm using the variable y to indicate f of x. So the function itself is y equals 2x plus 3, but what we input into sim.solve is y minus the function. You can also equivalently write the function minus y. It's all the same. And then the variable that we want to solve for is x. Don't worry about this for now. That comes in later. Okay, and here I'm just getting out the first element, and that's just because, this ends up being a list. This is a list because sometimes there are multiple solutions to an equation, in which case you can get multiple solutions. We can actually see that here by squaring this. So here there are two solutions to this equation now because I've squared x, and those are both listed as elements of a list. Get rid of that. And so if we just want the solution itself and not the list, then you can just say 0 to get the first one. Okay, so here we get that the inverse function of 2x plus 3 is y minus 3 divided by 2. This is something that you can take a moment to confirm with a piece of paper and a pen. But notice that we have two symbolic variables here. So that's why we need to specify which variable to solve for. If you would solve for y, then, sorry, it's sy, not y, right? Then we simply get back 2x minus plus 3. This is trivial, right? Because we said y minus the function. So for solving for y, anyway, you get it. Okay, so this is the solution, and now we want to show that the composition of the function and its inverse just gives us back x. This needs to be the case if this really is the inverse of this function. Okay, so this line of code is literally just rewriting this line of code. I just set it to a variable. And here I'm using a substitution, so I show that when I substitute, so this is substituting a particular value of x for y, and then I substitute that from the inverse function back into the original function. And we should get 4 because that's what we put in. So we set x equals 4, we plugged it through the inverse, we plugged it through the function, and we got back 4. And here it's the other way around. Maybe I'll even change this just so you see that it works for any other number. Again, what I'm doing here is substituting for x the value, the number 42, wherever x appears in the original function. And then whatever value that happens to be, we can calculate it, but it doesn't matter. Whatever that outcome is, that value gets substituted back into y for the inverse function. And if this inv really is the inverse of fun, then we should get exactly the same number back. And we do. Okay, great. So that was the most of the exercise. And now what I want to do is rerun this, but for a different function. And so the question is, what's going to happen? And is sim.solve still going to give us a valid inverse solution for this function, 2x plus the sine of x? Okay, so what happens is we get an error. And the error is that no algorithms are implemented to solve this particular equation. So what does that mean? Well, it can mean one of two things. It can mean that the equation itself is literally unsolvable. There is no solution to this equation. That can happen if there are just inconsistencies. Imagine a equation that says this. There's no solution to this equation. Or it's possible that there are solutions to the equation, but SymPy is just not able to identify them. Exercise 22 is your opportunity to explore and solidify your understanding of function symmetry. So as I described in this chapter, functions can be even or odd. Those are both ways of being symmetric, or neither. And what do those mean? Well, if a function is even symmetric, then if you input x and if you input minus x, the output of the function is identical. So that would be even symmetric. If a function is odd symmetric, then when you input minus x, you would get minus f of x. And if it's neither, then and it's neither of those things, then f of x and f of minus x are just different numbers altogether. Okay, so here's what you want to do. There's actually two parts to this exercise. I will first describe and show the results for part 1. This is exploring symmetry for specific numerical values using NumPy. And then in part 2, we will generalize this exploration to move from arithmetic confirmation of function symmetry to algebraic confirmation of symmetry using symbolic variables. Okay, but I'll talk about that later. So what you want to do here is design 3 functions. So come up with 3 functions. One is even, one is odd, and one is neither. Now, I am going to show you my functions in a moment in Python. You can take a sneak look at the functions I used, but I encourage you to come up with your own solution. So any one even function, odd function, and function that is non-symmetric. Okay, and then the arithmetic confirmation is basically to plug in specific values of x and then minus x, and then see what it looks like. Okay, so I used 3 values for x, 1, 2, and pi. So for the even function, I inputted 1, and I got an output of 0. And then I inputted minus 1, and then I got an output of 0. Okay, so same output. Okay, then for the odd function, when I input 1, I got 2.83. And when I input minus 1, I get the magnitude of the number is the same, but the sign flips. So that means that g of x equals minus g of minus x. Okay, and then for the function that is non-symmetric, well, you input 1 and minus 1, and you get completely different values. So this is a non-symmetric function. Okay, and then what I've discussed in the book is that confirming or evaluating function symmetry arithmetically by inputting individual numbers is great. That's good for building intuition. That's good for seeing examples and demonstrations. The problem with that approach is that it can be misleading because you can have specific values that give very specific the appearance of function symmetry, but it's just an exception for that one numerical value. And here you see an example of that. So this function, I inputted 1 and -1, but I got 0 in both cases. Now, uh, that's difficult to evaluate because 0 doesn't have a plus and minus. So this particular example with this particular number does not actually really confirm that this function is symmetric, because even non-symmetric functions can be 0 for different numerical values, and that doesn't tell us that much. Okay, so that's why we confirm it with multiple numbers. So these three sets of rows are coming from exactly the same code, exactly the same functions. I'm just evaluating one up here and then two and then pi. So here are the three functions that I came up with. The even function, I have the absolute value of x cubed minus x squared. Now, x cubed on its own actually is an odd function, but if we take the absolute value, it becomes an even function. So we have two terms in this even function, both of which are even, so the function itself is even. Here I have an odd function. This is x cubed again, and then times the sine function. And as I discussed earlier in this chapter, the sine function is an odd function. And here I have a function that is neither. Now, e to the minus x squared and the log of the absolute value of x, these are both even functions on their own, but notice that I'm shifting x over here. So now this becomes a non-symmetric function. In fact, shifting by x is often the easiest way to make a symmetric function non-symmetric, especially if you have x in here multiple times and it's only shifted once. Okay, so then here I list the three different x-axis values that I'm going to use to evaluate. And here you see, so this is, I'm just looping over these different x values. And here I'm just printing out some text where I input the, so for the even function, x, and then f of minus x. So this is f of x, this is f of minus x. And here we can see evaluating that function for the even function, the odd function, and for the non-symmetric function. And yeah, then this just reproduces the results. Again, the key point is that for all of the, or for the even function, any value or any of these three values that I input, the result is the same. The output of the function is the same, regardless of whether I input plus x or minus x. And for an odd function, the magnitude of the number is the same, but the sign flips. And for the odd function, or for the non-symmetric function, we just get different values altogether. Okay, now for part 2 of this exercise. We want to basically just re-implement this in SymPy, but now instead of using individual numbers, which is like the arithmetic approach to demonstrating or evaluating function symmetry, instead we are going to use an algebraic approach. So instead of substituting individual numbers, you want to substitute minus x for x. And now you're using these as symbolic variables in SymPy. And then I printed out all of the results to look like this. So here we have the even function. You can see I wrote f of x. So this is just the definition of the function. Here I input f of minus x, and we see what happens. And what happens is we get exactly the same thing. And then here is minus f of x. Now this minus the function is not the same thing as the original function. Okay, but that is fine because that's not what we care about for even functions. That third line here is relevant for odd functions. So here's the odd function. Here's, again, g of x is just the definition of the function. G of minus x, and here you see that the terms are the same, but the signs are swapped. Now, both of these signs are swapped, and so that means that minus the function is the same thing as the function of minus x, right? So these two lines are the same, and these two lines are different. That is the key distinguishing factor between even functions and odd functions. And then we have the non-symmetric function, and here basically what you want to look for is that none of these three lines are equal to each other, so they're all different from each other. Some of the, I mean, here these two terms are the same, that's fine, but you can see here we have e, and then in the exponent there's a plus x, and here it's a minus x. So all of these three terms are just different from each other. So this is non-symmetric. Here's how that looks in code. Here I'll just create a new symbolic variable, and I call it x. This is the even function, the odd function, and the non-symmetric function, or neither. And now coding this stuff isn't very difficult. You just want to be mindful that you're always using the SymPy functions and not the NumPy functions. So you don't want to do that. This would be incorrect. You want to make sure that these are symbolic functions coming from the SymPy library. Okay, and then here I'm just printing out f of x, and I'm using LaTeX coding. So I get the LaTeX. This gives me LaTeX code, and then the math and display functions together will transform that raw LaTeX code into a beautiful display that we can look at in this notebook. So the original function here, I'm substituting for x, I'm substituting minus x, and here is the minus of the function. So plus x would be in here, but it's minus f of x. Okay, so and then we run that, and that just reproduces the figure that I showed in the book. Well, this was a pretty long chapter with a lot of exercises, a lot of coding exercises. So I thought I would close out this chapter exercises with two exercises that are not so difficult. There's not a whole lot of like new math concepts, although I guess a little bit in the next exercise. But anyway, certainly this one, exercise 23, this is just, a bit lighter, just to give you a little bit more experience working with NumPy and Matplotlib and translating formulas that you see in a math text into Python code. So basically, all you want to do is look at these expressions, implement them in NumPy, and then plot them with Matplotlib. Pretty straightforward. So I chose to use a plotting domain of -pi to 2pi. Of course, you can explore that and change it. Here's the function definition. Here is the label that I use for plotting and the line color that I use for plotting. And then here I just loop through all of the different elements in this list. You can see I create this as a list here. And then I plot them. So yeah, the code is pretty straightforward. There's not a whole lot to do in terms of math. I just think these plots look nice, and I hope you do too. Okay, that was the first three, and then I have the next three over here. It's always quite interesting to see what happens when you embed one trig function inside another trig function. Okay, so that looks like this. So now, I encourage you to play around and have fun, explore. Maybe you want to embed more functions. How about like numpy.exp of the natural log of x squared? I'm just making this stuff up. There's nothing. Of course, now the label here is wrong. But let's see, that ends up being this one. Well, it looks pretty interesting. And here we are with exercise 24. This one is about exploring the log function for complex valued numbers. Now, I mentioned earlier in the text and also in the previous chapter that the logarithm function is not defined for negative numbers. Now, that is only true when we are limiting ourselves to real valued numbers. If we consider complex valued numbers, then we actually can take the log of a negative number, and it ends up being a complex valued number. Here you see I have a really, really short intro to complex valued numbers. Now, complex analysis, which is like kind of like calculus, but involving complex numbers in the complex plane, that is a fascinating and beautiful and really visually appealing topic in mathematics. I don't talk about complex numbers in this book, except for a few cases where it happens to produce really interesting looking graphs. And this is one of those cases. Okay, so what you are going to do in this exercise is create a graph that looks like this. It's a little bit like the Nightmare Before Christmas or something. There's something very spooky about this. Okay, what are we looking at here? Well, what we're looking at is the iterated logarithms of a number. So here's how that works. You take a number, so let's say we start with 2, for example, and then you take the natural log of 2. Now, y is going to be whatever it is, and then you take the natural log of that, and then you take the natural log of that, and the natural log of that, and that, and that, and that, and so on. So, written out in one expression, it looks like this. It's iterated logarithms where you start from one number, which you can kind of think of as a seed. Okay, so then what I did to create this plot is start at some number that I picked randomly. So I just randomly select a number and not so Python is randomly picking a number between zero point 0.1 and 3, and then it's taking the log 20 successive times. So it's like this, but 20 of these things. So you take the log of the log of the log of the log and so on up to 20 times, and all the way in the middle is whatever this random number happened to be. Okay. And then you store all of those results. Now, eventually, that's going to become you're going to take the log of a negative number quite quickly because basically, as soon as this dips below 1, the log of a or the log of a positive number between 0 and 1 is negative. So, and then the log of that negative number is going to be a complex valued number. Okay, so you store all 20 of those complex numbers, and then you plot them in the complex plane. So complex plane is like a Cartesian plane. We have the real part on the x-axis and the imaginary part on the y-axis. Okay, so what I just described, the procedure I just described, produces one line in this vortex here. So then you repeat that whole procedure 100 times. That's why you see all these lines. So there's 100 lines in here, and each of these lines is generated by exactly the same little iterative algorithm, but starting from a different randomly selected number between zero point 0.1 and 3. Okay, so that is how you get this plot. And it's pretty remarkable. It's beautiful, actually, that it no matter where you start from, it always converges to the same point here. This is called a fixed point. It's something that you would learn about in a course or book on complex analysis. It's basically the solution to this equation. So there is some value of z, complex number z, where the natural log of z equals z. And that is basically whatever this happens to be. The real part is like, I don't know, zero point 0.2, and the imaginary part is 1.3 or something like that. Again, you don't need to worry about the mathematics here. This is just about gaining some more experience working with numbers and math functions and visualization in Matplotlib and for loops and so on. Just more experience with math coding. So here you see, let's see. So here I initialize a vector of 20 numbers. And this is one potentially tricky point here that you need to tell NumPy specifically that you want these to be complex valued numbers. Otherwise, if you don't specify the data type, then this is just going to be real valued numbers, and Python will discard the imaginary parts, and you'll get a warning message. Okay, so here I loop over 100 iterations, 100 runs, and then here's where I generate a new random number between 0.1 and 3. Okay, and then here's the for loop where we run this iteration. Very simple. You just take the log of the previous number, right? So we start off here taking the log of some random number, and then we take the log of that, and the log of that, and the log of that, and so on. And here's where I extract the real part to plot and the imaginary part to plot. And yeah, then that's how it is. And then, yeah, here I just have some random colors specified. So I hope you found this interesting, and I hope you enjoy coding this up. If you like, you can try changing more things. You can make this be systematically varying numbers, starting points, instead of randomly selecting a number. You can try different ranges of numbers. You can try changing the colors of the lines and so on. All sorts of interesting stuff you can play around with.